Hello, and welcome to this FMSP online revision session. This session is looking at the MEI Further Pure 1 specification and the topic of proof and series. We'll start by looking at the specification and seeing what you need to know. You need to be confident with mathematical induction and able to produce correct proofs. You need to know that a sequence is an ordered series of numbers, an ordered set of numbers, and a series is a sum of a sequence. And you need to be able to sum simple series. There are three methods and we will look at each of them. And you need to know that a series converges, or a sequence converges, if it tends towards a particular value as the number of terms increases. Some really important points. This applies to other topics but is particularly relevant to this one. If the question says use a particular method, you will not get any marks at all if you use a different method. A little more subtle, if a question says hence, then you must use your previous answer to continue. If you try and do it by a different method, again, you won't get any marks at all. And more subtle still, if a question says hence or otherwise, then you can use any method you like to continue. But there's a really big hint there that the work that you have already done will make everything much easier. So the three methods that you need to be confident with. We'll look at each of these in turn. For standard results, you should know the formula for the sum of consecutive numbers. That's the formula for triangle numbers, of course, and you need to memorise that one. The sums of squares and cubes are in the formula book. Do make sure that you copy carefully when you need to use them. Then there's the method of differences. This is quite straightforward, but the crucial thing is to make sure that you set your work out clearly so that you can see which terms are cancelling. And finally, proof by induction. There is always a question on this, and it's usually worth 6 or 7 marks, which is 9%. That's almost a whole grade. So it's really worth being confident with this method and making sure that you check carefully with the mark scheme to know exactly what you need to put in. There's not much to memorise for these topics. You just need to do lots of practice. So let's have a look at some questions. This question says, use standard series formulae, so the method is specified. It's a show that question, so you need to make sure that you've got plenty of clear working. But the answer is given to you, so that means that when you get to the end of the question, you can check that you've got it right and be pretty confident that if you've shown enough working, you'll get full marks. So let's work through this. It's a show that question, so let's be really careful and formal about this. Start by writing down the left-hand side. The first step then is to multiply out the brackets. And I've still got brackets around that because you're summing the whole of that expression. Then split your expression into the three separate terms. The sum from 1 to n of r squared, take away the sum from 1 to n of r, take away the sum from 1 to n of 6. Then copy carefully. First of all, the sum of the squares, 1/6 n, n plus 1, 2n plus 1, minus 1/2, this is the formula that you need to remember, n plus 1. And then minus 6n. Don't forget that, it's 6 plus 6 plus 6 n times, so that's 6n. We've then got to work at getting it into the format that's given. And a good strategy to start with is to get the fractions out the front so they're not in the way. So you might be confident about doing this and can do it straight away, but here's a little way that might help. Change them all into 6, so that half becomes 3/6 and that 6 becomes 36/6. then you can take out 1/6. And each term also has an n in, and if you look at the thing that we're aiming for up here, then you can see you need a factor of n at the front. So that leaves us with n plus 1, 2n plus 1, minus 3n plus 1, minus 36. And now, if we multiply out and collect terms, everything should fall out and end up with the answer that's given. So multiply out the first brackets, 2n squared plus 3n plus 1, and then the second bracket, take away 3n, take away 3, take away 36. That's 1/6 n into 2n squared. The 3n and minus 3n cancel, minus 38. Take out a factor of 2, and I've got my n squared minus 19, and then my fraction cancels to 1/3 n squared minus 19, as required. Let's see how the mark scheme works for this question. There is a method mark for multiplying out the bracket and separating it into 3 sums. There are then 2 accuracy marks for using the formulae correctly, -1 each error, so you need to get 2 of them right to get the first mark and all 3 of them right to get the second. There's then a method mark for a valid attempt to factorise, to take out that factor of n. There is an accuracy mark for a correct expression at the end, and then there's another accuracy mark for a complete, convincing argument. So that if it's, if you get down to the bottom with the right expression, then yes, you get that first accuracy mark. But if it's been a little bit wobbly, or it's not quite clear, or you've been a bit sloppy with your use of brackets and that sort of thing, then you won't get that extra mark. Okay, let's have a look at proof by induction. So here again, method specified. Okay, first step, dealing with n equals 1. If n equals 1, the left-hand side is 1 times 2, and the right-hand side is 1 times 1 plus 1, which is 2, times 1 plus 2, which is 3, all over 3, and both of those equal 2. So you then can say left-hand side equals right-hand side, so result is true for n equals 1. I'm going to talk about the mark scheme as I go through with this one because it's particularly important with the proof by induction questions. So that's 1 mark for all of that. It's quite a lot, but it's not terribly difficult. Okay, the next step is to write down, assume result is true for n equals k. And that is the first of your explanation marks. Note that you're assuming the result is true for n equals k. You're not assuming that n is equal to k, because obviously we want this result to be true for all values of n. So it's truth that we're looking at rather than what n is. Now, it's always a good idea to translate that statement into algebra and say what you actually mean by it. What I mean by it is that 1 times 2 plus 2 times 3 plus all the way up to k times k plus 1 is equal to k plus 1, k plus 2, all over 3. The next step is to look at n equals k plus 1. So I'm going to add a term to each side of this. So it was originally up to k plus 1, and now I'm going to add on k plus 1, k plus 2. And as always, I need to do the same thing to both sides of my equation. Okay, the next step is to try and make this look like the form that I'm aiming for up at the top there. And it's sometimes worth just putting a note to this side saying what you're aiming for. Don't put this as part of your proof because it's the last line, but just as a little note to yourself, I want k plus 1 in there, so that'll be k plus 1, k plus 2, k plus 3, all over 3. So that's just a little note to self. Okay, so I need a factor of 3, so let's start by taking that out. So that'll be 3/3, and when you've taken a fraction out, always check, mentally put it back in again and make sure that you haven't made any mistakes. And then if you look at both terms, I've got a k plus 1 and a k plus 2. Sorry, k plus 1 first and k plus 2 in both terms, which is good news when you look at what you're aiming for. And then I've got k plus 3. And gosh, I'm there already. This was quite an easy one. So let's be really pedantic and write it as k plus 1 and then k plus 1 plus 1 and then k plus 1 plus 2. So those square brackets are obviously not mathematically necessary, but they really show that I've got it exactly in the right form, and I can then say which is the required result for n equals k plus 1. And I need to talk about marks for that section. So there is a method mark for adding the k plus 1th term, and there is an accuracy mark for getting down to that correct expression there. And then we need to finish off carefully. Therefore, if the result is true for n equals k, then it is also true for n equals k plus 1. Since it is true for n equals 1 by induction, it is true for all positive integers n. And there are 2 marks for that final bit. 1 mark for saying if the result is true for n equals k, then it's also true for n equals k plus 1, and a final explanation mark which is dependent on the previous one, to say since it's true for n equals 1, by induction it's true for all positive integers n. So that is proof by induction, and do make sure that you do plenty of practice and that you check the mark scheme and make sure that you really are putting everything in that you need. Finally, a question on method of differences. First thing to notice is that part 1 says verify. If you've already completed or are working towards your A2 in maths, then you may already have met the method for partial fractions. And you should note that you don't have to do a complete partial fractions method for this. All you have to do is check that the right hand side is equal to the left hand side by taking that right hand side and doing the addition. If you've not, if you're still in year 12 and you haven't done partial fractions, then don't worry about it at all. You don't need it. Then it says use the method of differences, so you have to use that method, and obviously it's using what you've done in part 1. Then it says write down the limit to which it converges, so it's only worth 1 mark, so that should be really obvious. And then the last bit, take care that sum begins at 50. Okay, let's tackle the different parts of this. So the first step is verify. So I'm going to start with the right hand side because it's easier to merge separate things into a single term than to separate them out. I'm going to put the whole lot over r plus 1, r plus 2. So I've multiplied r by r plus 1 and r plus 2. The second term I've multiplied by r and r plus 2, and the third term I've multiplied by r and r plus 1. Multiplying that lot out, I get 2r squared plus 6r plus 4 minus 3r squared minus 6r plus r squared plus r, and 2r squared plus r squared minus 3r squared cancels, 6r and minus 6r cancel, and I'm left, oh, I haven't put my denominator in yet. I'm left, as I hoped, with 4 plus r plus 1, r plus 2. It is important that you put that denominator in on each line. It is a verify question, so they're looking at working, and if you miss that out, they might not give you all of the marks. Okay, the mark scheme for this says method 1 for an attempt at a common denominator and accuracy 1 for convincingly shown. Can't spell convincingly shown. Okay, so it does need to be set out correctly. Then use the method of differences. So it's show that, so again I need to be very careful with my working. Should be anyway. Sum from 1 to n of 4 plus r, r plus 1, r plus 2 equals, well, it equals the sum from 1 equals r to n of what you just showed that was equal to. So 2 over r minus 3 over r plus 1 over r plus 2. And now you start doing terms. So don't simplify, because simplifying tends to hide the patterns. So 2 over 1 minus 3 over 2 plus 1 over 3. And then if r is 2, 2 over 2 minus 3 over 3 plus 1 over 4. And if r is 3, plus 2 over 3 minus 3 over 4 plus 1 over 5. And I can see that things are cancelling out, so I can do dot 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 and do my last 3 terms. So that's r equals n minus 2. So that's 2 over n minus 2 minus 3 over n minus 1 plus 1 over n. And then r equals n plus 1 plus 2 over n minus 1 plus minus 3 over n plus 1 over n plus 1, and then r equals n plus 2 over n minus 3 over n plus 1 plus 1 over n plus 2. And now we find that everything within these square brackets cancels out. And I'm left with 1 plus 2 minus 1.5 is 1.5, so that's 3 over 2. 1 over n plus 1 minus 3 over n plus 1 is minus 2 over n plus 1 plus 1 over n plus 2. And I don't need to do any further work because that's the result I was given, so as required. Okay, let's look and see how the mark scheme works for this question. A method mark for applying the given result. A method mark for the first term and at least one more. 2 accuracy marks for at least 3 consecutive correct terms. Somewhere in there. A method mark for attempting to cancel, at which point you must have some algebraic terms, and another accuracy mark for the whole thing being convincing. Okay, write down the limit. Now, it does say write down, so you can just write down the answer and get the marks, but you can also put some thinking about this. You've just shown that that is equal to 3 over 2 minus 2 over n plus 1 plus 1 over n plus 2. And as n gets very, very large, that tends to 0 and that tends to 0. So the limit as n tends to infinity is what you're left with on the end, 3 over 2. That's just worth 1 mark. And part 4. Now there's a bit of a hint here. Giving your answer to 3 significant figures is not going to come out as a whole number. So the first thing to do is to split that into 2 parts very carefully. The first part goes from 1 to 100, so that's easy enough. And then I need to think, well, what do I need to take off that in order to be left with a sum from 50 to 100? Well, I want 50, so I must make sure I only take off up to 49. Okay, now I use my result. Okay, now the sum, I'm just going to write it down here. You won't have this problem in the exam because it will all be on the same page. This was the result that you had. So, if n is 100, that's 3 over 2 minus 2 over 101 plus 1 over 102. And I'm subtracting, and I'm going to put it in brackets to make sure I subtract everything, 3 over 2 minus 2 over, now n is 49, so that's 2 over 50 plus 1 over 51. So you can see that the 3 over 2's cancel, and I'm left with minus 2 over 101 plus 1 over 102 plus 2 over 50 minus 1 over 51. At which point I reach for my calculator, plug those in and get this out. It's worth writing it down to a few more places, and then rounding that to 3 significant figures is 0.0104. And the mark scheme for this, there is a method mark for splitting it up into 2 parts. There's then another mark for using part 2 rather than starting again, and an accuracy mark for getting that exactly right to 3 significant figures. Okay, we've got one more question to look at. It's another proof by induction question, and this is one on sequences rather than sum, so a slightly different approach. But it's proof by induction, so that's the only method that will be allowed. So I'll use a different slide where I've got a little bit more space to work. So first step, as always, if n equals 1, u1 is equal to 2 to the 1 plus 1 plus 1, which is 4 plus 1, which is 5. which is the given value. You're told that U1 is 5. So the result is true for n equals 1. And as before, that is worth 1 mark. Next step, assume result is true for n equals k. Exactly as before. You need to write that down just like that for your first explanation mark. It's then worth writing, i.e. you are assuming that UK is equal to 2 to the k plus 1 plus 1. From that you say, well, UK plus 1, the definition you're given is UK plus 2 to the k plus 1. That's what you're given up there. And you're now going to substitute in the value for UK which you had, which is 2 to the k plus 1 plus 1, and then you're adding on 2 to the k plus 1. So I've got 2 lots of 2 to the k plus 1 plus 1, and that of course is 2 to the k plus 2. And to be really pedantic, we'll say that's 2 to the k plus 1 plus 1, which is the required result for n equals k plus 1. So for that part of the working, there is a method mark for using UK and an accuracy mark for getting the correct expression. And then we need to finish off exactly as before. Therefore, if the result is true for n equals k, then it is also true for n equals k plus 1. Since it is true for n equals 1, by induction, it is true for all positive integers n. And as before, we have 2 marks, one for the first sentence there and one for the second. And as before, these are dependent. The second one is dependent on the first, and the first one is dependent on everything else being right. So there isn't any point in writing that final part if you haven't managed to complete the actual algebraic bit, but if you've done the algebraic bit, you must write those extra bits in order to get all of the marks. Well, that's all you need to know for series and proof. I look forward to your company in the other MEI FP1 videos and wish you all the best with your exams. Goodbye.